As you can see in this figure, water waves coming from a large body of water having a parallel arrangement to the shoreline. When interfere with a small slit, it takes a different form. That waves have a different form of propagation pattern. So diffraction is essentially simply it is a bending of wave, but it have some other conditions to follow. For in case if this instead of this wave that you are seeing here, if a large wave like a tsunami wave comes across this small slit, will it be able to bend that tsunami wave as we have shown in this figure? It will not be able to, because that slit is so small compared to that wave to make an effective bend or curve in the propagation pattern of that tsunami wave. On the other case, if a small leaf falls into the water body and it makes a small wave, that small wave passing through this slit will make a change in this in its propagation path, as we have shown in this figure? Essentially no, because that wave is so small compared to the slit to make a big change in its propagation pattern. And as we can see, by analyzing the nature of the wave that have changed its pattern, we can analyze the nature of the slit it have crossed by. So if we taking this example to the microscopic level, to analyze a crystal, we can allow some kind of waves to fall on the crystal and analyze the change in its propagation pattern of that waves coming out of the crystal, to study about the nature of that crystal. So about how the electrons are arranged, how the electron density and probability to find electrons in that crystal or its planes can be analyzed using a outcoming wave from a crystal. So in fact, can we use any kind of waves to analyze that crystal, or as we have shown in this example, a very small wave coming from a leaf, or a large wave like a tsunami wave will not make any significant changes while it passes through this small slit. So essentially we have to use, if we have to analyze some kind of crystal, we should have a wave of that property that's comparable to the size of that slit. So the wave must be of that wavelength that's comparable to the size of the slit. So as we have shown here, a wave that's comparable to the size of this slit in this water body was able to make a bend after passing through this slit. So essentially if we have to analyze a crystal, we have to use some wave that have a wavelength that's comparable to the size of that crystal, or those waves should be of the size, or should be of the wavelength that is in line with or comparable with the interplanar spacing of different planes that are present in the crystal. Now we will look into it in detail in the Bragg's law. So very commonly X-rays are used to analyze crystals. So why not UV rays, or why not visible light is used to crystals? So the answer is, X-rays have those wavelengths that's comparable to the size of the interplanar distance of crystals. Interplanar distance are of the order of angstroms. So X-rays have those wavelengths that are comparable to angstrom level wavelengths. So they are used to analyze crystals. To understand Bragg's law, let's consider X-rays. X-rays falling onto a crystal, and these are planes, crystal planes, different crystal planes, like 100. Let's take it. So 100 plane, parallel planes, 100 parallel planes aligned inside the crystal, and X-rays are falling onto the crystals, and these X-rays are making an angle theta with the crystal planes, and they are reflecting from the crystal planes, and we are analyzing the output from these crystal planes here. If we have to obtain a diffraction pattern as the output of the X-rays from the crystal, we have some conditions to follow. And I told you earlier why we have taken X-rays to be used as a tool to analyze crystals. So here we have the interplanar distance d, and this interplanar distance d and the wavelength of X-rays are comparable or similar size. So we opted to analyze crystals using X-rays. Now we have the first ray here and the second ray here. So if we have to form a diffraction pattern here, we should obtain we have to follow some conditions, and the first condition is the path length between these two rays, the first ray and second ray, should be a multiple of wavelength lambda of the X-ray, should be an integral multiple of wavelength lambda of the X-rays. So we have to check whether the path length and the path difference that you can see here between the two rays. This is the first ray and second ray. The path difference between the two rays is this much. The second ray follows this much extra path when compared to the first ray. So we have to measure this distance. So to measure this distance, we have angle theta that this X-ray makes with the plane, and we have this angle theta. So this much distance can be d is the interplanar distance, so this much difference between the d sine theta, and again same distance comes here, again one d sine theta comes here. So the total path difference between these two rays total path difference between these two rays will be 2d sine theta, and if that is equal to n lambda, integral multiple of n lambda, constructive interference will take place, and a diffraction pattern can be obtained as output from the crystal. Okay, but as we can see, this condition is satisfied. The Bragg's law. This is called the Bragg's law, and this condition to be satisfied here is lambda is less than or equal to 2d. Okay, 2d is the interplanar distance. So 2 times interplanar distance is the maximum allowed limit to the wavelength of the kind of ray we are using to analyze our crystals. So that's the first condition, and next condition is this equation can be obtained only when this condition is a consequence of periodicity of the crystal or periodicity of the lattice. Okay, so lattice is some imaginary points located in space. They have a periodic arrangement. So they are imaginary points. So if we add some, if we place some atoms or molecules in this lattice, we obtain a crystal structure. Okay, we obtain crystal structure. So this periodic arrangement of lattice causes this creation. This plane essentially shows the periodic arrangement of atoms. These planes are periodic arrangement of these planes are made by periodic arrangement of atoms. So this diffraction condition that we have, diffraction condition and the Bragg's law and the diffraction pattern that we have obtained here is a consequence of this periodic arrangement of atoms in the crystal and the planes that are formed by this crystal. And these planes doesn't refer to the composition of atoms in the lattice point. So this is an output of an X-ray diffraction pattern, and as you can see, it's intensity versus scattering angle plot. But it doesn't show it doesn't give any information about the type of atoms that are present in the crystal. And what we have is some peaks. That peaks gives information about the planes that are available, the kind of planes that are periodically available inside the crystal. So so why these different peaks have different intensity, and why some peaks are big, some peaks are small. In order to understand why some peaks are big, why some peaks are small, we have to introduce two new concepts. One is reciprocal lattice and the other is Fourier transform. So now we will try to understand what reciprocal lattice is and what Fourier transform is, and then we will come back to Bragg's law and continue thereon. So in order to understand what Fourier transform is, we have Fourier himself on the left, and on the right we have Fourier transform of the image of Fourier. And now we are going to see what this picture tells us. So Fourier transform is essentially a shift from time domain to frequency domain. And on the left side we can see a square wave, and that's a time domain wave, a time domain square wave. And this square wave is composed of a large number of frequencies. This square wave is a mix of a large number of frequencies, and they have some frequencies that are dominating and some frequencies that are very small. So in a Fourier transform, we are unpacking that large set of frequencies. We are unpacking that large number of frequencies that are that this square wave composed of, and we are transforming that data about that large number of frequencies into a space known as K space or a Fourier space. You have seen the image of Fourier, and it's on Fourier transform. So another major feature of Fourier transform is that any kind of wave, any kind of periodic wave, can be expressed as a sum of sine waves. So Fourier transform, I told you earlier that Fourier transform is unpacking a wave into a large number of waves, and these waves and these large number of waves can be sine waves. So or sine waves of different amplitude, frequency and phase can be mixed together to obtain the final kind of wave that we require. In this figure we are adding a large number of frequencies and obtaining a final wave, and by continuing this process again and again with large number of frequencies, adding them, we obtain a square wave. As we have shown earlier, the square wave the reverse process happens in a Fourier transform. A square wave in time domain can be unpacked into those large number of frequencies that we have added here in the Fourier transform. A good animation about the Fourier transform is added on the description box, so you can refer to it. So here we can see in the Fourier space there is an origin at the center of that K space image of the Fourier transform of the image that you are seeing on the right. I have center, and I told you earlier that this shows a K space, and K is essentially K is equal to 2 pi by lambda, and it have an inverse relation with related to the wavelength, so it will have a direct relation with frequency. So higher the frequency, we have higher frequency points or higher frequency components of the Fourier transform will be denoted by white dots that are far from the origin, from the center, and the low frequency components of the Fourier low frequency Fourier components will be denoted by the white dots that are closer to the origin. Now we are trying to unpack the frequency component and try to understand how the high frequency component and low frequency component look like, and how we are trying to separate between the high frequency components and low frequency components, and try to analyze the difference between two. Okay, here we are doing the reverse process. Here we are taking only the low frequency components denoted by the white dots around the origin, and trying to reconstruct the Fourier image, the image of the Fourier, so the real image. Okay, here we can see the Fourier's image, but its details are missing. We are not able to see the fine details of that image. Even though we can see the image on as a whole, we are unable to see the fine details, that wrinkles on the coat, or details on the hair. We are unable to see the higher frequency components or higher details. Now we are looking at the higher frequency components only, and ignoring the low frequency components that are around the origin. Now we are able to see only the higher frequency or higher frequency components of the image of the image. Okay, we are trying to reconstruct image from the Fourier image, or from the Fourier transform. Okay, here we see only the higher frequency components, and low frequency details are missing. But the higher frequency, even though we are missing the image as a whole, we have the higher frequency components of the real. The higher frequency detailings of the original images are preserved here. The pattern on the hair, the wrinkles on the coat, etc. are preserved here, even though we are losing the image as a whole. Okay, here on the top we can see a Fourier transform of some images of some flowers, and on the bottom side we can see, here on the bottom side, on the bottom left, we have taken the Fourier transform. We have taken that part of the Fourier transform on the top right, and taken a very small portion of that top right Fourier transform image, and we have tried to reconstruct the original image. And since we have taken only a very small part, we are not able to see the fine details of the real image, but as a whole we can see some rough layout of the original image. And if we take a higher radii of or a higher portion of the original Fourier transform of the original image, we will be able to reconstruct the original image in full details. I hope you can relate it to the image editing softwares that we are using in our phones or laptops. Their contrast or sharpness or blurriness, everything that you apply there is an application of the Fourier transform. Essentially, image is converted into a Fourier transform, and the manipulations that you are doing are worked out on a Fourier space. So here essentially what you see is blurring of the image, blurring of the real image. That happens when the k-space of the original image, or the Fourier transform of the original image, is minimized to a very small portion of the k-space around the origin. Okay. So why should we learn about Fourier transform while analyzing a crystal's structure? Okay. Here you can see some stripes, alternate dark and white stripes, and on the top, and on the bottom side we can see the image, the Fourier transform of those images. So on the right side you can see some slanting stripes, and its Fourier transform is given as two white dots on a black surface on the bottom right. Okay, so we- what we have seen these images before, because these stripes are essentially diffraction patterns that you obtain from, or we can, at least we can relate these stripes as diffraction patterns that we have obtained from the X-rays that are coming out of the crystal. So if the images on the top are diffraction patterns of the X-rays coming out of the crystal, and on the bottom side see the we see the Fourier transform of that diffracted images. Okay, on the bottom we see the Fourier transform of the diffracted outputs that we obtain from an X-ray diffraction pattern. Here you can see English alphabets A, B, C, D, and their own Fourier transform. The image A are written in various styles on the top, and they have almost same Fourier transforms. And for B, C, D, and they have different kinds of Fourier transforms. From this, we can infer, what we can infer is that different types of planes in a crystal, different types of planes, 100, 110, 111, different kind of planes will have a different kind of Fourier transform. So we will be able to know what kind of crystals are, or what kind of planes are present inside that crystal. This is another image, and the corresponding Fourier transforms are shown on the right. Now let's try to understand what a reciprocal lattice is. Here a sodium chloride lattice is shown, and here as we can see, there are many planes exist in this lattice, and you can see four figures here, and all those planes exist in the same lattice. So if we want to represent all those planes in this lattice in a single picture, it will be very difficult to recognize each and every planes that exist in this lattice. So we need some form of representation that's convenient to represent different kinds of planes that exist on a lattice. So therefore we adopt a new kind of technique, that is reciprocal lattice, to show different kinds of planes that exist in a crystal structure, a crystal lattice, in a more convenient and easy way. Here we can see different kinds of planes that exist on a crystal lattice. There are many 100 planes, many 110 planes exist on a lattice, so it will be very difficult to represent these planes on a normal way, so we adopt the reciprocal lattice technique. In these many planes, these many 200 planes can be reduced to just one point in the reciprocal lattice. Here you can see different planes like 101, 102, 100, etc., and their corresponding reciprocal lattice points in the reciprocal space, and each black dot denotes a reciprocal lattice point. As I told you earlier, that reciprocal lattice is a representation of lattice planes in a much simpler way. So here we are trying to construct a reciprocal lattice from the direct lattice planes, like these planes available to us. Okay, this is a 001 plane, this is a 111 plane. Okay, So in order to construct a reciprocal lattice, first we have to choose a common origin, um, and the origin can be chosen as per our convenience. So uh, we can choose an origin of our convenience, then draw a normal to each plane from the common origin. So first we choose an origin, then we draw a normal to each plane from the common origin, and the length of that normal should be 1 by DHKL, and D is the interplanar distance. So I will demonstrate one example here. So first we have to choose a common origin. So I choose this point as a common origin. This can be any point, this point, or you can choose here, or it is our convenience to choose from our origin. Okay, now I choose this point as my origin, and now I draw a normal to this plane. Okay, from this origin I am drawing a normal to this plane, 0, 0, 1 plane, and this normal should have a distance, should have a length of 1 by 1 by d 1 by dHKL, um, should be the length of this normal. Okay, so I have drawn a normal to this 0, 0, 1 plane, having a length of 1 by dHKL. So I denote this point as the reciprocal lattice point corresponding to this 0, 0, 1 plane. So if I have another plane like this, in this direct lattice, so I have another plane like this, this can be denoted by 0, 0, 2 plane. Okay, so this plane to corresponding to this plane, I will have a reciprocal lattice uh, at some larger distance like here, but on the same line to this normal, because the interplanar distance. So I have in the first condition I have this plane. I try to draw a reciprocal lattice to this plane. So the interplanar distance is this much. This much is the interplanar distance DHKL. This much is the interplanar distance. I took the inverse of that to obtain the reciprocal lattice point here. Now, for this plane, the interplanar distance will be this much only. Okay, a smaller d. So 1 by DHKL will be a higher length. So I obtain a reciprocal lattice point here. So likewise, for a 1, 1, 1, 1 plane, also we can draw reciprocal lattice points. Okay, first I choose an origin, then draw a normal to the plane having a length 1 by DHKL, and the next plane might come here. So interplanar distance will be this much, and at 1 by DHKL distance I obtain a point, and that will be my reciprocal lattice point corresponding to 1, 1 plane in direct lattice. To sum up, we have seen these 4 things in this class. First of all, what's direct lattice? Direct lattice consists of imaginary points, periodic imaginary points, and when we place some atoms in these imaginary points, we obtain a crystal lattice. Okay, then we saw what Bragg's law. And Bragg's law, we show the diffraction emergence of diffraction pattern while formed by reflections from different lattice planes. And in Fourier analysis, we have transformed from time domain to transformed an image or some planes, or we saw some stripes like this, we saw some image, and we transformed this into K space, or Fourier space, or frequency space, and in this space they can be denoted as dots or points in a K space. We have an origin. Okay, then we saw what A reciprocal lattice. Reciprocal lattice is transforming normal planes, direct lattice planes, or crystal lattice planes into a more convenient and more easy representation. So we are transforming somehow a set of parallel planes like 100 planes into just a point in the reciprocal lattice. So I've told you earlier how this is worked out. Okay, now how to relate these four. So a direct lattice is a Fourier transform. If we take a direct lattice and if we take its Fourier transform, we can obtain a reciprocal lattice. Okay, so essentially that is what's happening here. You can see different types of planes are here. They are components of the direct lattice, and when we analyze, when we Fourier analyze this, when we or Fourier, when we taking the Fourier transform of this direct lattice, we obtain a set of points in K space. We obtain a set of points in K space, and that points are the reciprocal lattice points that we have earlier obtained. Now let's consider diffraction pattern. Okay, uh, while analyzing some crystal planes, and when we take the diffraction pattern of that planes or diffraction pattern of that crystal, what we are doing is making the reciprocal is making a Fourier analysis, or the process we are doing is a Fourier analysis, or a physical process, or we are doing a physical Fourier analysis by taking a diffraction pattern of a crystal. So I hope you can make a connection between these four concepts, and in the coming videos we will try to explore more about the scattering wave amplitude and diffraction conditions. Thank you.